Welcome to our session 8, Weatherford College Interdisciplinary Conference. This Friday morning. Thank you for coming here to learn more about the mycorrhizal fungi and the cover crops. So today we have two beautiful ladies, Yvonne, Byrd, and she is a biology major here at the Weatherford College. And she wants to be an environmental advocate and wants to go to join the EPA, Environmental Protection Agency. And here, the lady we have, Anya Mims, and she wants to be a herpetologist. Do you know what the herpetologists do?
Study plants.
Reptiles and amphibians. Herpetologist. So she wants to do more on frogs and lizards, some reptiles and amphibians. Maybe conservation side of that, right? Okay. So they'll be presenting on the one of the projects we are doing here on campus at the farm. And they did a symbiotic relationship between the mycorrhizal fungi and the cover crops. So they look at the effects of the different cover crops on the mycorrhizal fungi. So I'm going to hand this to them. Let's welcome.
And now, to first get into this relationship between mycorrhizal fungi and cover crops, we'll get into what are cover crops. The cover crop is a plant that is grown for the benefit of the soil rather than for what it produces, such as, wheat for your bread or cotton for your fibers to make clothing. The cover crops aren't for any of that. And typically they will be grown during the winter after the fields will stop producing. Some examples include ryegrass, oats, crimson clover, blue stem, and of course there are many others. And they are beneficial to both farmers and the environment. And why do we use cover crops? Well, first, they help stop soil erosion. The main reason of that being they have roots that digs down into the soil and holds it there. But of course, even a dead plant just lying across the ground will help keep the soil sitting there because the wind will have to blow and move the plants away first. And well, if it's a much heavier plant, such as say a tree on a log, the only way the wind could even move that log is if it was a tornado. And other things they do is improve soil quality. So as mentioned, you had when they eventually die, you have dead plants will eventually decompose and become part of the soil itself, typically through everyone's little favorite landfill isopods, roly-polies, and other little bugs. And of course, we'll minimize weeds because, you have all these cover crops around. There is no space for the weeds to grow. They will end up being choked out. They also enhance water availability because as it rains, even if the plants are dead, that water, when it gets down beneath them, it can't evaporate. It can't get evaporate and escape out into the air because it is too dark down there. It's covered by the plants, such as if you have a pile of dead leaves, the tops might be all dry and crunchy, but of course when you start raking them, the bottom is all nice and wet. And then they will also increase biodiversity because, of course, first of all, you have all these different types of plants, and that will attract a variety of different types of animals, bugs, reptiles, mammals, birds. And they will also reduce the need for herbicides, pesticides, and fertilizers, mainly because if one plant is getting under attack by, say, bugs, it will simply send out a chemical signal and warn the other plants hey, I'm under attack, up your defenses. Such as if you ever mowed your grass, that lovely cut grass smell, you of course smell, that is the grass trying to alert the other grass that it's under attack. Of course, that is ineffective against lawnmowers. And of course, life without cover crops is one we have experienced before here in the United States of America in the 1930s with the Dust Bowl. An entire area like this, completely dust covered. Such as you could have sandstorms like this and completely burying things. One could argue that this novels about the Great Depression and the Dust Bowl, such as The Grapes of Wrath, can barely sort of show how awful this stuff was. And of course, it was a direct result of poor farming practices and drought. Some of those farming practices included just plowing the land and leaving the soil completely just bare. Nothing on it, remove all of the plant matter from it, dead or alive. And of course, one of the main problems problems, of course, with the farming practices was the plowing of all the prairie grasses. These prairie grasses had very, very deep roots compared to, say, the wheat that was grown. These roots were so deep that cattle could come through and graze on it, they'd grow right back. A big fire could come and burn through it all, and of course the roots were so deep they remained unscarred and grow back. And of course for the droughts, that was the main reason for the Dust Bowl, all of these deep roots in the prairie grasses could let them access more water deep down in the soil. And so the prairie grasses, they could withstand all of the harshness of life here in the Midwest. The wheat could not. And when the drought hit, it all died, crumbled to dust, and was blown away. This left topsoil exposed and unprotected. Ultimately, there were 5.2 million acres of these deep-rooted prairie grasses that were plowed. And the Dust Bowl, when it came through, essentially transformed the Great Plains into infertile layers of glowing dust. And eventually, under President FDR, the federal government began to aggressively push farmers to adopt new methods of plowing that would help restore the topsoil. One of these being that they would leave such as like unused plant matter, such as the stalk of the corn, just there on the ground to help hold the soil down, and then of course later decompose and improve the nutrient quality of the soil. And another way was the reintroduction of native grasses to the soil. However, one of the methods used for a cover crop was called wheatgrass, and it could thrive in harsher conditions. However, it would ultimately outcompete other plants and cause a monoculture. And monoculture is of course bad because you need biodiversity to have a balanced ecosystem. Because with your monoculture, you have but one plant, and they will all bloom basically around the same time. And of course, when this bloom dies off, there's no food for your pollinators. Like, this is a current problem today that our honeybees, our native bees, and other native pollinators, such as butterflies, hummingbirds, and a couple of different species of bats, can face today because, well, when the blooms die, no food. And of course, they themselves will die or will have to migrate somewhere else, and whatever, say, preys upon them will also have to either die or move somewhere else. And this is why our study included a mixed array of different species, both native and foreign. And cover crop variety will also help increase carbon sequestration and arbuscular mycorrhizal fungal colonization. Now, what is this mycorrhizal fungi exactly? Well, the literal meaning of the word is just fungus root. It is a symbiotic fungus that will integrate itself into the roots of plants to help increase their surface area. And all fungi are heterotrophic, meaning they can't produce their own food. They must get it from another source, such as, unless any of you here in the audience are mycologists, you have your decomposing fungi that you might see growing just on your wooden fence. You'll have parasitic fungi, such as the ever notorious cordyceps, which for those of you that don't know what cordyceps is a parasitic fungus that affects insects and other types of arthropods, such as spiders. And then, of course, you have your mutualistic fungi, such as the mycorrhiza. And there are two types of this mycorrhizal fungi, your ectomycorrhiza and then your endomycorrhiza, which is then subdivided into two categories, such as your dark septate endophyte, or DSE, and then your arbuscular mycorrhiza. And over 90% of all plant species will form these mycorrhizal associations. And plants colonized by these mycorrhizal fungi will outcompete other plants. And we study on the arbuscular mycorrhizal fungi because it is far more prevalent than the dark septate endophyte. And why is the mycorrhizal fungi so important? The arbuscular mycorrhizal fungi, of course, as previously mentioned, will colonize plant roots and can increase the surface area of those roots up to 1,000 times, allowing them to absorb more water and immobile nutrients such as phosphorus, zinc, and copper. And these extra nutrients will, of course, allow plants to grow a lot larger and at a much faster rate than ones uncolonized. Such as you can see here with these two basils. If you look very closely, you can see that this one has a lot more colonization, and of course the plant is a lot bigger, it's a lot leafier, a lot better looking. You have the smaller one over here. There's like barely, you can't really see any of the roots from it at all, and of course the plant is a lot smaller and just looks a bit worse. And as for the colonization process, the spore will germinate, sort of similar to how like a plant seed might, and it will send out an extra radical hyphate to locate a plant root, and then when it locates the root, it will create an acrosorium. And then from the acrosorium, it will start forming structures within the plant's root, such as a coil here, has some hyphae to get through the plant, intracellular hyphae specifically, can form arbuscules, which are little tree-like structures, and vesicles. And of course, here is a root that has no fungal body in it. Here's one with a variety of different structures. And of course, here's your extracellular hyphae forming an aphrosorium to get within the roots, and what it does can form things such as these vesicles. And the vesicle is used for mainly, it is storage for like winter or in times of hardship such as a drought. And then down here you have your arbuscules, which help increase surface area between the fungus and the plant. And it is not on this slide, but coils, as will act fairly similar to the arbuscule and help increase surface area. And here are the coils right there. And we had our own little study just on the Weatherford College farm, and we'll now hand this off to Evie.
Okay, so to study the mycorrhizal fungi response to cover crop, we plant a variety of native and foreign grasses to the Weatherford College farm. Here we have a 300-acre, this is our Weatherford College farm, and of that we took a 32-acre plot. This plot is plowed every year, so the soil is already aerated, which allows the oxygen to reach the soil, and it allows the roots of the plant to kind of like work its way through the soil easier. It's less compact. So agricultural plants are premised to show higher levels of the mycorrhizal colonization following the cover crops. The effectiveness of these cover crops and which perform best are not very studied, so that is what our study is focusing on. We subdivided 5 plots. We labeled them A, B, C, D, and E. Plot A contained all of our native grasses. That included the little blue stem, big blue stem, switchgrass, side oats, partridge pea, and springletop. And plot B contained our William lovegrass and beadle blue stem. These are both foreign grasses that were introduced into the United States about 100 years ago. And plot C, we planted Bermuda grass. It is an invasive species, so we left it to its own vices. And plot D contained wheatgrass and legumes, or winter wheat, and plot E was our control. So we collected 3 soil core samples from each experimental plot after the cover crops were planted. The arbuscular mycorrhizal spores and plant roots were then extracted from the soil, and the samples were stored in a fridge for later use. So here we have the native grass was planted on May 26th, and barely over a week later, there's increased vegetation and there's no soil exposed, so it's better for the soil. Okay, so the first step to processing the soil is through soil sieving. We sieved the soil through 4 sieves, measured 500, 250, 150, bottom to top. The 500, of course, is these are measured in micrometers. So the 500 are larger holes, so it catches all the debris and the roots and everything, which we collect those and store in a 50% alcohol solution for later use. So we sieve the soil through all of these sieves. The soil and spore contents are trapped in the bottom 2 sieves. They're the smallest holes. That's the 50 and the 100 micrometers. Those are the only holes small enough to catch all the spores. Okay, so the next step is through centrifuging. Basically, we collect the spores and centrifuge them at 2,000 RPM for 1 minute, so all the spores can settle at the bottom of the vial. The supernatant, which is a muddy water, it's just the excess materials we don't need, so we pour that out. And then we just have these spores that are still submerged in some sediment, so we add a 50% super solution and centrifuge the mixture again at 2,000 RPM. Just to spin the spores in the solution. The centrifuge just settles the material, so everything else is just surface. The resulting supernatant was then filtered through a 45 micrometer mesh and rinsed with tap water. So all the spores are basically now cleansed and all the sediment's gone, so it's just spores and clean water. We then add them to a 50 milliliter vial, and we fill the water level to 20 milliliters. So now you just have a 20 milliliter solution. We take a dropper, we pull out 1 milliliter. So we're testing 1 milliliter out of the 20. and then we suspend it. We take that and place it onto a petri dish. It's a 6x6 grid. We place one drop in each little square, and then we quantify them under a 40 times magnification to find the spore density. So we only count the live spores, the dead spores are ignored, and then we take the 2 subsamples from each vial just for consistency purposes. Okay, so once the roots are extracted, we have to process them. So we bring them 5 to 10 times in tap water, and then we add a 5 to 10% of potassium hydroxide solution. The clear roots are then cooled and bring in tap water 5 to 10 more times, and then we treat them with a 0.1% colazerol black E, which is a staining reagent. This allows us to see the roots better underneath the microscope. And then we heat them for 80 to 100 degrees for 1 hour. The stained roots are then cooled and the CBE is drained from the container, and then we add a 50% glycerol for the destaining. Here we have the oven. Okay, now we prepare the slides. We pick the most desirable fine-haired roots. They go on the cover glass a lot more easily than thick roots. We gently press it to flatten the root but not damage it. And then we prepare 2 slides for each root sample. Okay, so here we have the field of view. This is our microscope. Anything that intersects this field of view, which is considered the crosshair, is counted. So we're focusing on finding hypha, arbuscule, vesicle, or coils in the view. We use a 200 times magnification to find these. So anything that overlaps the crosshair is counted. Anything outside the crosshair is considered biased, so we ignore that. And then we repeated these steps for each slide for 100 field of view, just to determine the percent colonization. Okay, here is our spore density results. As you can see, native mix and the control are significantly higher than plot C and D. Plot A, that's the native mix, and the control, they measure 9.55 and 8.94 respectively. And then here we have 4.34 and 5.03. The probability is like 0.05, so that's our baseline. So anything above that isn't considered significant. So this is only a slightly significant variation between the cover plots. Here we have the hypocolonization. The hypocolonization is important because this is the first thing that the spore makes. And it also helps extend everything else that happened after, all the propagules, like the vesicle, the coils, arbuscules. This is the starting point. It is found to be significantly higher in plots A and B again, with plot A being 45.17 and plot E being 43.83, compared to plot B, which is only 31.17. So the probability here is 0.002. That's significantly higher than 0.05. So there's a slightly more significant difference in the hypocolonization than the spore. Here we have the arbuscule colonization. Despite the limited percent colonization, arbuscule is very important because it increases the surface area. This allows the nutrient exchange, the chemical signaling between the 2 symbionts, that's the plant and the mycorrhiza. We did not find any significant difference in arbuscule colonization among the treatment plots, and this is probably because the arbuscule is hypersensitive, so it is easily destroyed and created. And we also took these soil core samples in spring, so they probably weren't needed as much as during winter times. So here we have the vesicular and the coil colonization. That's also, the probability is less than 0.05, so it's not significantly different. It looks like it, but we took 2 samples from each experimental plot, so this is considered noise. One sample may have tested higher, but the other one did not, so it's not a significant difference. Okay, so in discussion, the spore density and hypocolonization were significantly higher on the native plant mix and the control plots. This suggests that the native plants and or allowing them to grow will increase the spores and the mycorrhizal hypha. This will help to further crop plant yield. The increased crop yield following cover crops might be linked to the increased access to the soil nutrients aided by the mycorrhiza. We did expect the increased mycorrhiza fungi in the experimental plots after the cover crops were planted. So in conclusion, through our study, we found that planting the native grasses or letting them plant and letting the native plants to grow as cover crops will help to increase the mycorrhizal spores. Further studies should focus on the nutrients because we did not do that. We weren't testing for the nutrients, so that is something to consider next time anybody does a study. So you would be testing for the nitrogen, the phosphorus, and the potassium to see if it correlates with the mycorrhizal fungi. This study should help farmers to select which type of cover crops increase the mycorrhizal fungi and agricultural lands for better crop yields.
What got you interested in doing this research? Or either one of you?
Well, we're going to Utah and Alaska. That was a big incentive, but it's part of our career plan, so it will help further us in our career.
So you will be presenting your research in Alaska?
Yes,
That's so cool.
and Utah. Utah's first.
How would you go about presenting agriculture?
Well, there was a thing called the Three Sisters, which is from the Native Americans, actually, that they would grow corn, which sort of acted as like a trellis, because they would then grow these climbing beans, which would climb up the cornstalk, and of course winter squash to act as ground cover. You could, like, say, instead of just having these huge fields of corn, because that is one of the main monocultures I can think of, you could also mix in your beans and your squash with them as well, just creating biodiversity.
So, I have an HOA, and I'm not allowed to do, corn, all this other stuff. What can you do in your own garden, I guess, is what I'm saying, to bring back the bees and all that other stuff?
Oh,
Simply, you can just plant like a mix of flowers that your HOA wouldn't mind, such as like different types of wildflowers, such as at my own house. I am planning on growing like a blue bonnets, both the blue kind and also the red kind we can also find around here. So find like different types of flowers that your HOA wouldn't mind you planting, and then just plant those.
Okay.
butterflies and bees love the color purple.
And then red will attract hummingbirds.
Why do y'all keep the roots?
Good question.
Is a part of getting the dye to take to them?
Yeah, maybe. Basically, whenever you make a clay pot, you heat it up to conserve all the materials. Any question?
So basically, we want mycorrhizal fungi in all of our plants and food to make more product, right?
Yeah, the plants don't have to work as hard because they're acting as, a relationship. They're exchanging nutrients for each other, so the fungi don't have to work as hard, and neither does the plant.
Is there any way you can sprinkle the fungi or something on your plants that already is there?
They make a mix, yeah. It comes in like a package. What's it called?
There was I think some myco extreme
Yeah,
stuff, but
Yeah,
you don't
that's
sprinkle it on the plants, you would
Mix
mix
it
it in
in
with the
the
soil.
Yeah. But I'm sure we get there eventually.
Well, there are a lot of commercial products these days. Like farmers using like billions of dollars on these commercial products, and that they use in the cornfield, soybean, all this. And this is also a way to go organic. Like we're using a lot
Without
of
using
the
pesticides and
inorganic fertilizers, and we actually
Outside
killing
of it.
those mycorrhizal fungi. So if you want to go organic, then that's the mycorrhizal fungi. They can help get the nutrients out of the soil.
So what got you interested in going for a career for the EPA?
Right, well, because, most recently, the legislations have kind of gutted any environmental regulations and conservation methods, so.
So you're against Trump?
Answer that.
This is not a government.
Some things, yes.
And if you were to choose to plant more native grasses, where would you find those?
Typically, you can do some looking online. Like I'm getting a whole bunch of different wildflower seeds, and I just looked online, like places like Etsy. Just like do your research and make sure you online first to make sure the exact seed you're buying is native to this area. So you don't want to introduce like an invasive species.
Cheerios is actually sending people wildflower seeds. Yeah.
There's a company called American Seed Company that's really, really good at this.
And we have a Native Plant Society of Texas
Yeah.
too. And then you can reach out to them and they'll help
Yeah,
you.
sometimes they do plant cells.
Yeah.
That and native prairies maybe do that too.
The Weatherford, they have one, the Weatherford chapter.
Chapter
They'll
has one.
do that
Yeah.
in Weatherford. Any other questions?
My question's not really related to your research, but what got you into the field that you wanted to go into, Anya?
I just think lizards are pretty interesting because, you know, we have those little house geckos. I always used to love catching them and looking at them and keep them in like little terrariums, like observe them further. So I figured out that they can actually squawk. They're a local species, they will have arguments with each other. Because even in terrariums, sometimes I would hear,
Right.
they sound very cute. And they're also super cute because you'll find them finger sized. They actually do not, that is actually the adult size. They will not get longer than your fingers.
So those with the lizards you'll be focusing on?
No, I'm just planning on, I want to be like a field herpetologist, so I'll be focusing on like a wider variety of different like lizards, reptiles, amphibians.
Good. All right, let's